So today I'm gonna be explaining another great article from again Mirella, this great scholar, which is compositional generalization via semantic parsing. Exactly this article. So if you like this article, I predict that with high probability you will also like these articles from Tel Aviv, Allen Institute, and so great places. Uh, we use GeoQuery dataset, and this article is really interesting. It uses again the paradigm of expectation maximization. I have a playlist for expectation maximization in NLP that I'm collecting all of the papers and I explain all of them. You see that expectation maximization is really good when you have a latent variable that we usually need it in natural language processing because supervised learning is expensive, and also we don't have that training data for everything. That's why we need to infer something about the latent variable, and that's the motivation for that. So we are using the GeoQuery dataset, and so for example, what is the density of Texas? This is the training set, and you can say it's select density from state where state name is Texas. So the idea is we decompose the coding into two phases where an input utterance is first tagged with semantic symbols representing the meaning of individual words. This is like the article that I've written about using universal semantic tag dataset, and I used CRF LSTM for semantic tags, universal semantic tag dataset, which is a good dataset from a university in Netherlands. And but here they use it. They see that this tag as just a latent variable, and because sometimes we don't have that training data to learn those tags, so they consider training those tags as those symbols. Let's say here they call the word symbols instead of semantic tags. They call it semantic symbols, and then we infer what are those semantic symbols are. And so two phases. The first one is a tag with semantic symbols representing meaning of individual words. So we have some words, and so this is an LSTM, for example. So each of these words has a semantic tag, and for the first stage is to just model it as a latent variable. Then in the second stage, a sequence-to-sequence model is used to predict the final meaning representation. This meaning representation is that semantic thing. For example, the logical form, the lambda calculus, any meaning representation that you're working. And for example, if you're working in SQL or a SparkQL or any other meaning that you need to prepare, then this is the meaning. And the data sets, they use GeoQuery and, for example, parse give me the large state. Answer A is the largest of A of state. So it's a nested thing. And if this is an example from GeoGraph graph database, geography, and so sentence could be what is the biggest city in a state name 0, and this is the meaning of that, which is a SQL query if you're working with a relational database. And there are other datasets as well. This one, ATIS, is very popular. jQuery and ATIS is very simple, very interesting, and there are also other uh, data sets such as Scholar, Advising, and Drop. So this is the model architecture. As I said, we consider this tagging as this here as is a latent variable. It's z. So these are z. What is the probability of latent variable given your utterance? Your utterance is Columbus to Chicago one way on Thursday, and but finally, what you are looking at the end of the day is this logical form. So just a sequence to sequence model, it's very easy. Once you know Z, then this sequence of Z goes to another sequence, which is the meaning, final meaning, we call it Y. And so this is the relationship between the meaning, for example, this is the lambda calculus, and X is your utterance. So now here in the middle layer is Z. So we just multiply with these probabilities. So it finally gives the probability of a logical form given your utterance, your sentence. For example, Z1, Zn is a tag sequence of X. And every tag is a symbol. So the semantic tagging, they use this just a linear operation on the hidden state and the word, and you then finally use softmax. And because we have n independent of these probabilities, because you have an input sentence of length n, for example, your utterance is x1, x2 to xn, so n is the length of the sentence. That's why you're multiplying all of these probabilities, because you assume independence as well. And then this is a standard. Use the forward and backward of the LSTM in order to make a better representation, because if it is backward, you also know from the future, and it is more meaningful. You can represent. It's more, let's say, expressive. And the meaning representation, this example, so X is your utterance, and Z is a middle layer. As I said, it's just the latent variable, but this latent variable uses the symbol S. And finally, what you're looking at is Y. This Y is something that you have the training data of that. And at least in this paper, they have these logical forms. Or instead of lambda calculus, meaning in the form of a lambda calculus, you could have the SQL format of that. But so this paradigm works for all different meanings. Either it is SQL, it is SparkQL, it is lambda calculus. Any meaning representation can be handled with this sequence to sequence model. So E is a semantic tag, but this one is the word embedding. So we augment them. So instead of just word embedding, we also augmenting it with that tag embedding. That's why it becomes more expressive. So that if you give this to that sequence to sequence model, it can represent your logical form much better. So tagging learning is just an expectation maximization. That's that paradigm that I've explained. And for entity linking, for some symbols, it is rather straightforward to determine the corresponding alignments based on the results of the entity linking. And so we thus find the following two rules to automatically align symbols to words in an utterance. So these two rules is, the first rule is that for lambda calculus, if a predicate takes only one entity as an argument, and this entity can be linked to a word or phrase in the utterance, we assume there is an alignment between them. And second, for SQL expressions, if the entity in a filter clause can be linked to an expression in the utterance. Again, we align the column to the linguistic expression. And so now we use the expectation maximization. So what is the probability of a symbol given your utterance? You just marginalize over A, and P of A is just a uniform prior. And finally, you get the this probability of symbol given your utterance. Now we are able to exactly compute the posterior probability of each alignment. You know, it's sequence to sequence model. You need an alignment. So this is the posterior probability of an alignment. Because in this alignment, you have also the latent variable and you multiply it by your alignment. So if alignment can be induced in advance via entity linking, we can manually set the value of this Pij. And for soft expectation maximization, these alignments are then directly used to train the tagger. But in the hard expectation maximization, we replace pi with pi tilde as a training objective to perform the hard EM updates. So this is how we train the tagger. So this is the expectation step, because you're inferring what is your possible latent variable. And once you know that latent variable, you just fix that latent variable, and together with your utterance, you have a good meaning representation. And you get the parameters of this probability function, and that's it.